Now it's time to talk about some antiderivatives of a few of the trigonometric functions. So let's say, for example, we want to, and I'll start out easy here, we want to find the function whose derivative is cosine. So this, remember, this is notation for this. So I'll say, okay, let's say f of theta is equal to some function whose derivative is this inside guy. That's what this stands for. Okay, so this right here is equal to the function. Actually, I'll write it like this. We're trying to find the function or the family of functions, because there's going to be an infinite amount of these. To find the family of functions whose derivative is the integrand. We'll just say the inside. Okay, so we want a situation where when we take f prime of theta, I just use theta here because we could just as easily use x or whatever we want to. So f prime, there's got to be a function out there. When I take its derivative, I get cosine theta. So the question is, what is this function? What is f? Well, whose derivative is cosine? Well, it's pretty easy. We know that if we differentiate sine plus some constant, we get cosine. So if we let f, large F, be sine theta plus c, then that implies that the derivative of this guy is equal to the cosine. And that's perfect. That's what we want. We want it to be the inside. So we say that the integral, the indefinite integral of cosine theta d theta, that's equal to the sine of theta plus some constant of integration, just like that. So right now I've shown you the first antiderivative. So if you have for your integrand, if you have cosine, we work our way backward to this right here. Okay, so let's look at a couple more here. So that this would be antiderivative rule number 1. Okay, let's work on antiderivative rule number 2. So let's say we've got the integral of sine theta d theta. Now again, I'm using thetas here because that's consistent with your book. You can use x's, t's, whatever you want to use. It doesn't matter. Okay. So what we're looking for, this by the way, is some function f of theta, and that's the guy we're looking for. We want a situation where when we take the derivative of f, we get this inside guy. Okay, so we got to think, what function, when we take its derivative, do we get sine? Well, we're pretty close if we take the derivative of cosine. So watch. Let's say we let f of theta be equal to cosine theta plus some constant, right? So we get the whole family of functions here. Well, that would imply that the derivative of this guy, well, that's equal to negative sine theta. But we want it to be equal to sine theta, so watch what we'll do. We will just go like this. Since we want it to be equal to sine theta, we'll just multiply both sides by negative 1. So if we do that, then we get this, and working backward, then we get that this should be equal to negative f of theta, which would be equal to negative cosine theta minus c, but it's really irrelevant whether we add c or subtract c, because c could be positive or negative. It's just a constant. So what we get here is a situation where what we want is this guy right here. So what we're going to do is we're going to let our large f, instead of being equal to cosine theta plus c, we're just going to let it be equal to negative cosine theta plus c. So the argument goes like this. We'll just let it equal negative cosine plus c, because now when we differentiate, we get negative sine theta, which of course is equal to just sine theta, the integrand part that we were looking for. So in general, we have this. If we integrate sine theta d theta, we really ask, where did sine come from? What function had a derivative of sine? And we know that that would be negative cosine theta, and then we add the constant of integration at the end because we want the whole family of functions. So we'll call that guy antiderivative rule for the tangent, or for the trigonometric functions, number 2. So let's keep going. We've got 4 more to do. And you might say, well, let's go ahead and find the integral of, let's say, secant theta d theta. Well, that's not as easy to find because we don't, off the top of our heads, know which trig function we would differentiate to get secant. So what instead we do is we take a look at the functions that we know. So we know that one of the trig functions has a derivative of secant squared, and we know that that comes from tangent. And if we take the derivative of tangent, we get secant squared. So that means the antiderivative of secant squared, working in reverse, would take us back to tangent. Okay, so there's rule number 3. And so we can go through and get all these other rules. Okay, so we know that if we have the tangent of an angle times the secant of an angle, working backward, what function has a derivative equal to this? And we know that that is secant. So if we differentiate secant, we get tangent theta times secant theta. Okay, a couple more. We know cosecant theta. Well, what function? And here's where we have to be a little bit careful. The function that we have to differentiate to get this is not quite clear. Okay, so here's what we know. We know this one's not quite as easy to see, I don't think. So we know if we take cotangent theta, the derivative of cotangent is cosecant squared, but negative. Okay, so if we go like this and we take the derivative, we get positive cosecant squared theta. So it's not quite as easy to see, okay, because we're used to taking the negative. But if you just put the negative out front here, you'd be all right. Okay, so this will give us negative cotangent theta plus our constant of integration. And then, of course, we know that the derivative of cosecant is cotangent times cosecant. So that's, well, we know that the derivative of cosecant is negative cotangent, is negative cotangent cosecant. So if we put a negative here, we get our last rule. So those are the 6 trigonometric antiderivatives. These aren't the only ones, of course. We'll be working with more, but these are the first 6 that we can get very easily from looking at our differentiation.